is in Appendix A25. What page am I on now? 83. And so there's a pretty big table, table D3 in Appendix D on page A25, which compiles the acids here. And you'll find it here, hydrochloric acid, the Ka value is 2.9 times 10 minus 8. And then you'd set up the ice table, Ka acid plus water yields hydronium plus hypochlorite ion. There's also a Kb table here. The Kb table just has a mean here. And so means are typically shown in the Kb table. And, but if you need the Kb for other bases, you have to calculate them. All right, where did we leave off last time?
The strengths of oxo acid.
Okay. Take a look at that. Yeah, this is going to be, we could,
Today a holiday?
no, not a holiday today, but this is already a small class, so this is fine here. So when we're looking at the strength, we want, for acids, more positive charge on the hydrogen in a weak bond. When we look at oxo acids, the bond is all the same. It's an HO bond, HO bond. And so the bond strength is the same, roughly. Otherwise, we start looking at the bond strength. Now, if we want to figure out which one's a stronger acid, then we have to look for other things. And the other things would be polarity. And so the higher the positive charge on the hydrogen, the more acidic it is. And so acid strength depends on 3 things, and it depends on what the acid is. We might look at just one of them or all 3 of them. And so acid strength depends on the bond strength, the HA bond strength. The weaker the bond, the stronger the acid. Let me break off the H plus. It depends on bond polarity. The more positive charge on A, the stronger the acid. And so the higher the delta plus, equals stronger acid. Acid, as you call it, is H plus, so the more positive it is, the better. And then finally, it depends on the stability of the product. Well, the product is going to be 2 products. Hydronium, which is the same for all of them, and A minus. A minus would be the conjugate base. And it's going to be A minus aqueous. And so the more we can stabilize A minus aqueous, the more downhill it'll be, the stronger the acid. And so the more stable A minus aqueous is, the stronger the acid. And so this last point can be summarized like this. The stronger the acid, the weaker its conjugate base. And so this would be the conjugate base of the acid. Now, all these have the same bond strength, and we aren't going to look at the stability of the products yet for these. We're just going to look at the polarity. And so these are all going to be differences in polarity. Did I already talk about these?
Question. You said the stronger the acid, the weaker the conjugate base?
Yes. It's like this. You know, as acid strength increases, the base strength decreases. Did I talk about these already or not?
Yeah.
Okay. How about these, sulfuric versus sulfurous?
Yeah.
Yeah, okay. How about acetic acid versus ethanol? Did we talk about those? No. Okay, let's talk about those. So ethanol has what we call the hydroxyl group. And this is an alcohol group, and it's a COH group. But acetic acid has the same group. Which is the hydroxyl group. Ethanol is not really considered an acid. It's extremely weak, whereas acetic acid is orders of magnitude stronger. And so when we look at ethanol, the Ka for ethanol is 10 to the minus 16. The Ka for acetic acid is 10 to the minus 5. 10 to the minus 16 is worse than water, 100 times worse than water. And so we don't think of ethanol as a very good acid at all, but acetic acid is 10 to the minus 5, which is many, many orders of magnitude greater than water. And so what accounts for this difference? What accounts for this difference is what the hydroxyl group is attached to, but they're both attached to carbon. And so we have an HO and then we have a carbon, but the difference is what's attached to the carbon. And so what we're going to do is we're going to use oxidation states and formal charge and delta pluses and delta minuses to give us an idea of, are these electron rich or electron poor. And so looking at this here, is this carbon, it has no formal charge, but is this carbon electron rich or electron poor? Can you tell by looking at it? Well, one way you can tell by looking at it is a hydrocarbon. Hydrocarbons in general are electron rich. Hydrocarbons are flammable. Flammable substances are typically electron rich. And so over here, what makes this electron rich? Well, it doesn't look so rich. I mean, it looks like a normal carbon, but if we look at the oxidation state on that carbon, then we can see that it is electron rich compared to other carbons. So what is the oxidation state on this carbon here?
On which one?
This one.
43.
Okay, so I get 2, 4, 0, 1. So 2, 4, 5. So it would be minus 1. It has 1 extra electron. Well, let's compare that to this carbon. What's the oxidation state on this carbon? Okay, it would have 1 electron from here and none from these. So it's 1 electron. It's supposed to have 4 electrons.
Oh, so it's 3.
Plus 3, yeah. So there's a pretty big difference between these 2 carbons. This carbon is much more electron rich than this carbon here. Okay, now let's look at this. This is called the methyl group over here. If I have a methyl and this is a methylene group, or in other words, CH3CH2 is called ethyl group. And we have a methyl group here. Okay, what about this carbon? What's the oxidation state on this one? This would be 2, 4, 6, 7. It's supposed to have 4.
Plus 3.
Not plus.
I mean, minus 3.
Minus 3. Okay, this one's the same. This would be minus 3. 2, 4, 6, 7. Which gives us minus 3. And so we see a difference in this. We call this one electron withdrawing here, or not electron withdrawing, electron pushing, because it's electron rich, it pushes electron cloud density. And what that does is it pushes a negative charge density towards the oxygen, which in turn can push it more towards hydrogen. It makes this hydrogen a lot less positive. Whereas over here, this carbon is going to suck electron cloud density from the hydroxyl group, making this much more positive here. And so this is primarily due to polarity here. The other way of explaining it, there are many different ways we can explain the same thing. And the other way is we can use the inductive effect here. We have this oxygen, which is sucking electron cloud density away from the carbon, which in turn is going to force this oxygen to lose more of its cloud density than it normally would. Normally the arrow should point towards oxygen, like over here. The arrow is going to point towards oxygen, but these 2 carbons are different. If I have a carbon that's in the -1 state versus a carbon in the +3 state, the carbon in the +3 state is much more electron poor than the carbon in the -1 state, and so this makes this arrow flip in this sense. It might not completely flip, but there's going to be a much bigger struggle between these 2 in terms of electron cloud.
So because the carbons in acetic acid are electron rich, they're pulling away from the, the charge of the hydrogen,
Well,
making it less positive for me.
Making it less positive. In other words, there's a lot of negative charge here. That negative charge can spread out this way, making this one less positive. Whereas over here, there's more positive charge over here, which is going to suck the negative charge towards it, making this one more positive. And so we can see some more examples of this. So one example is this, chloroacetic acid. Acetic acid has a Ka of 10 to the -5. Chloroacetic acid has a Ka of 10 to the -3, which is like 100 times more acidic. So chloroacetic acid is quite a bit more acidic, and why would that be? So if we compare acetic acid here with chloroacetic acid, what's the difference? Well, what we did was we substituted chlorine for hydrogen. In terms of the inductive effect, now we're going to have 2 electron withdrawing atoms here. Chlorine's more electronegative than carbon, which is going to polarize the bond this way. And oxygen's more electronegative than carbon, which pulls electron cloud density that way. And so what we're going to do is even withdraw more of the negative charge density from the hydrogen. And that's going to make this hydrogen even more positive than that in acetic acid. And so if you're a base, like hydroxide is negative, and it's going to be attracted to positive. So this one will be the most attacked of the hydrogens versus these hydrogens here, which are going to be less attractive for hydroxide. All right, so let's take a look at what happened to the oxidation states. Now what's the oxidation state on this carbon here?
Which carbon?
This one.
So chlorine wins, right?
Yep.
So then carbons are on that one, so then it'd be 2, 4, and then it'd be 1, so that's 5, so it'd be +1. Minus 1.
Yeah, minus 1. So it's a lot less electron rich than it was before. And then we have this chlorine up here. And so that's going to make it more acidic. And so this is the chloroacetic acid. We also have another acid, which is borderline strong. Okay, what happens here? This is trichloroacetic acid. Trichloroacetic acid has a Ka 10 to the minus 1. 10 to the minus 1 is pretty strong, you know, as far as weak acids go, it's pretty strong. What makes it so strong? Well, different ways we can analyze it. One way is we can look at the inductive effect. The inductive effect here, now we have 3 chlorines sucking weight and 1 oxygen. And so that's going to withdraw negative charge density away from the hydroxyl group, making this one even more positive. And so if you're a hydroxide, you can really latch onto this hydrogen here. The other way of visualizing this is what's happening with the oxidation state. If we look at methyl, methyl has an oxidation state of -3, which is electron rich. This is methyl CH3. But if we look at this one, trichloromethyl, what's the oxidation state on carbon in trichloromethyl?
-3?
Not -3. It would be +3, yeah. Yeah, it's supposed to have 4, and it's missing 3. And so it comes out a deficit of 3, so +3. So when we think about methyl, it's electron rich. When we think about trichloromethyl, it's electron poor, just the opposite here. And if this is quite electron poor, it's going to suck in more electron density because now we got this. This one's also +3. And so we got these 2 +3 carbons sucking electron density into the structure. And so this is going to be the most acidic of this series. Yeah. Okay, let's compare acetic acid with octanoic acid here. Okay, so let's make the octanoic acid. Octanoic acid is going to have 1 methyl group, like this. That's a CH3 in the end. And that has these CH2s. CH2s are called methylene, and 6 methylene groups. And so methylene, this would be 1 CH2 group. The second one. So that's 1, 2, 3, 4, 5, 6. And then we'll have the COOH group. The COOH group is called a carboxyl group. Okay. And when we have this is, in organic chemistry, the COH is called alcohol. The C double bond is called the carbonyl group. And so when we have a carbonyl and the hydroxyl group on the same atom, we call it a carboxyl group. And this is a form of carboxylic acid. So both of these are carboxylic acids. So on one, we have 1 methyl group here. On the other, we have this octyl group here. Octa means 8 carbons. 8 carbons here. I think, yeah. No, 7 carbons in this. And the 8th one would be here. And so let's take a look at the oxidation states here. What's the oxidation state on this carbon? Do you guys remember? You got it? 2, 4, 5, 6, minus 2 is correct. How about this carbon? Do you guys remember?
I'm still trying to draw that. Close. That's also
Minus 2. In fact, all of these are minus 2. Except for the last one. What's the last one? Minus 3.
So you would say that group is pretty electron rich or electron poor? Electron rich.
And so electron rich groups we call electron pushers. And so this would be electron pushing group to the carboxyl. And so we look at what's attached to our carboxyl group, and it's pretty electron rich. Whereas when we look at this one, this group would be an electron pusher group. This group would not be an electron pusher. This group would be an electron sucker or electron withdrawing group. And so we have an electron withdrawing group or electron pushing group. This group would be electron, when we look at our carboxyl, this group is going to be electron pusher or electron withdrawer?
Push.
This is going to be electron pusher. Okay, now, that means if it's electron pusher, it's going to make it less acidic. And so it looks like this one should be a lot less acidic because it's got a lot of electron-rich carbons. And so it should be less acidic. And is that what we see? Well, when we look at the Ka, which one is more acidic? This is 1.8 times 10 to the minus 5. That's 1.3 times 10 to the minus 5. And the larger the Ka, the more acidic the acid is. And so acetic acid is more acidic. But is it significantly more acidic? I mean, 1.8 times 10 to the minus 5 versus 1.3 times 10 to the minus 5, it's not hugely different, is it? But it does turn out that this one is less acidic because this is a better pusher than this one, but you would expect this one to be a much better pusher of electron cloud density, but the impeding factor there is the distance, because, you know, these get further and further away. And so how much impact does this tail end carbon have in impacting the electron cloud density in the carboxyl group? It's going to have less and less impact the further and further away we get, but this is still better than this as an electron pusher, and we see that here in the acidity. Whereas this would be an electron withdrawal group attached to the carboxyl.
So acetic acid is an electron pusher.
The methyl, yeah, in acetic acid, we have the methyl group, which is an electron pusher. In trichloroacetic acid, we have an electron withdrawal group, and so it's going to make it more acidic. Here. Let's take a look at these two here. 1 versus 2. Which one is, well, both of these are chloro. You know, the chloro, we have a chlorine attached to this, so this would be chloroethyl here, ethyl being 2 carbons, and this would be like chloroethyl. And so chlorine would be an electron withdrawer, right? And so as far as the withdrawing effect, which one would have more impact? The chlorine here or chlorine here?
The chlorine on 2.
Yes, the chlorine on 2. Why is that? Because it's closer to this. And so this is going to have a bigger impact than having chlorine further away from this. In fact, In organic chemistry, we label the carbons. This would be like the alpha carbon, this would be the beta carbon. So if we have a chlorine on the alpha carbon, it's going to have a bigger impact than chlorine on the beta carbon here. So anyway, both of these should be more acidic than acetic acid, you think? Okay, let's look at base properties next. Actually, we'll do one more acid. We'll do a couple of more acids, actually. Let me skip this and then we'll look at acids. Now, alcohols like this are not very acidic. So we got this electron pushing group. We don't really have any electron withdrawing. Now, carboxyl group is going to be much more acidic because even though it has the alcohol, it has this carbonyl group, which is sucking electron density away. What's the oxidation state on the carbon? +3. Right? What's the oxidation state? -1. Right? So if we go to an alcohol like this, so let's take a look at two alcohols here. Look at. Okay. The two alcohols we'll look at, one will be have a ring like that, a 6-carbon ring. What would you, this is called the cyclohexane or cyclohexyl. This would be cyclohexanol. We call it cyclohexanol. What do you think about the cyclohexane ring? Is that going to be an electron pusher or an electron withdrawer? What do you think it'll be? Electron pusher or electron withdrawer? Well, when we think about hydrocarbons, hydrocarbons are very flammable. Like cyclohexane is very flammable. So even cyclohexanol is very flammable. So, flammable substances are electron rich. So hydrocarbons burn. Since hydrocarbons burn, we consider those electron rich substances. That's one way. So you'll think of this as being an electron pusher. The other way we could do it is based on the oxidation states. What are the oxidation states here on this carbon? So carbon versus hydrogen?
2.
Yeah, 2. And then here, none. Carbon versus carbon? 1. So 2, 3, 4. So this is 0. This carbon?
-2.
Yeah, 2, 4, 5, 6, -2. Same, -2, -2. So you'd expect this ring to be pretty electron rich. Even carbon in the 0 state is capable of losing 4 more electrons to get a +4 oxidation state. So, carbon in the 0 state would be electron rich. In one sense, not as rich as -2, but electron rich. So we would call this group an electron pusher or electron withdrawer. It's going to be electron pusher. And since this is electron pusher, it's going to make the acidity of this very low, right? And so the Ka for cyclohexanol is extremely low. In fact, I don't really consider it much of an acid. Now, we can contrast that with this.
So this was, that was called cyclohexanol.
Yes. I had the K for cyclohexanol. Was it? Take a quick peek here. Now, benzene ring is a very weird substituent. And so this is cyclohexanol. Benzene ring sometimes is called phenol. Like this. And we call this the phenyl group. And so we have a phenyl group here attached to an OH. And we call it phenol. The Ka for this is very small. Very small. The Ka for this, though, is quite a bit larger. This is like 10 to the minus 20. The Ka for this is 10 to the minus 10. Which means it's significantly stronger than cyclohexanol. And so, what could be causing that? Well, the benzene ring is very weird because the benzene ring turns out to be an electron withdrawal. And so this is an electron withdrawing group. This one is electron pushing group. Why is this one electron withdrawal? One reason is because of this. Benzene has a pi bonding network. That is, if I look at the pi bonds here, these are the p orbitals forming the pi bond. I see that these two overlap, and these two overlap, corresponding to the double bonds. But when we have alternating double, single, then what that means is that all of these can overlap. And so it's not just the ones that are forming the double bonds here, but all. And in fact, that's what we see for benzene. We see complete delocalization of the pi bonding electrons over the entire ring. Do you guys recall this in Chem 1A? Benzene, there's a whole section devoted to benzene and this, what we call a conjugated pi bonding network like this. And that goes for everything where we have alternating single, double bonds. We can delocalize the electrons in this fashion. And so what that means is there's room to accommodate electron density. And so the benzene ring is an electron withdrawer because it can suck electron density into the cloud here of charge. And so that's what makes this one so acidic. It's not a very acid. pKa is the power of the Ka. So the advantage of writing this as a power function is it takes up less space. So for example, here, how many sig figs is that? It's 2 sig figs. So for example, the Ka is actually 1.0 times 10 to the minus 10 at 25. And the pKa for this is going to be 10 to the power, and then we have 2 sig figs, so it's 10.00. So if we list it as a pKa, then it takes up less space than scientific notation. And so tables are often represented in power functions, but if they're represented in power functions, we have to do an extra step. You know, when we do an ice table, we can't use pKa's, we have to convert that into Ka, so we have to do an extra step here, reconverting this back to a Ka, and reconverting it back is just taking the antilog, which is 10 to the minus pKa power. And the pKa is just the negative log of the Ka. And so what happens here is this makes phenol much more acidic, because we're going to get a much larger delta plus there, a much higher polarity. Okay, what happens if we have a chlorine attached to the benzene ring? What does the chlorine do? Is a chlorine electron withdrawer or electron pusher? Chlorine's electron withdrawer, so what chlorine's going to do is it's going to suck even more electron density away from this, making this one more acidic or more acidic. And so the pKa should be lower or higher, or this is called ortho. Ortho, these two carbons are ortho because they're right adjacent. And so this would be the alpha carbons. And then the next carbons here are the meta, and the final carbon over here is the para. And so this would be alpha, beta, gamma. Now anyway, this is called orthochlorophenol, and its pKa should be lower or higher. Now it's flipped because of the negative, it's the negative. And so it's actually going to be lower. And so the lower the pKa, the stronger the acid. And so let's like 10 to the minus 10 versus 10 to the minus 9. 10 to the minus 9 is stronger. So lower, and that would be a 10 versus a 9 on pKa. And so we expect this one to be lower than phenol. So for acids, what we want to do is we want to maximize the positive charge on hydrogen. The more positive charge, the stronger the acid. And so we need electron withdrawing groups. For bases, we want to concentrate the negative charge. So we can compare two bases. We can compare hydroxide versus water. And so the difference between hydroxide and water is the amount of negative charge on the oxygen here. Hydroxide has a full negative charge given by the -1 formal charge shown here, whereas oxygen doesn't have a full negative charge. It has a partial negative charge. And so which one is going to be better? The one with a full negative charge is going to be better. And so the more concentrated the negative charge is, the better. And that's because acids react with bases. A base like hydroxide is going to be attracted to positive charge, and the more positive charge, the better. So for acids, we want positive charge. For bases, we want negative charge. And so let's take a look at amines. Amines are a class of organic bases, and there's a table of KBs for amines and NP. Let's look at some amines. Ammonia is an amine. Here. Methylamine is amine. So let's take a look at ammonia versus methylamine first. If we look at ammonia versus methylamine, we just remove one hydrogen and replace it with a methyl. A methyl group is an electron pusher group or electron withdrawer group? Electron pusher. And therefore, if it's an electron pusher, it should make the nitrogen more negative or less negative? More negative, which means it's a better base. The more negative, the better base. And we can see this in the pKb's. Over here, the pKb for ammonia is 474, which means the Kb is between 10 to the minus 4 and 10 to the minus 5. Over here for methylamine, the pKb is 3.38, which means the Kb is between 10 to the minus 3 and 10 to the minus 4. Well, a 10 to the minus 3 and 10 to the minus 4 is going to be better than a 10 to the minus 5. And so this is a stronger base. It's got an electron pusher. What about ethylamine? Should ethyl be a better electron pusher than a methyl or a worse electron pusher than a methyl? It should be better because this carbon is a minus, what is this one? Minus 2, 4, 5, minus 1. This carbon is a minus, oxidation state is minus 3. This carbon over here is minus 3. So we got a minus 1 and a minus 3 pushing electron cloud density to this. So there's more. But the effect is going to be tempered because the minus 3 is getting further away. So we got more electron rich here, 2 carbon atoms versus 1 carbon atom. But the distance is increasing. So it is just slightly more basic than this. And so ethyl is just slightly better electron pusher than methyl. And the longer the chain, the more electron rich carbons we add, but the further away they get from the amine part. Does that make sense?
So we need more carbon there, the more likely it is to be a better electron.
The more carbons there are, the more rich it is, and the better it is to be electron pusher. Electron pusher. And so the example that we saw earlier was this one. Acetic acid versus octanoic acid. If you compare acetic acid and octanoic acid, the more carbons there are, the better it should be as an electron withdrawer or electron pusher. Electron pusher. But for acids, do we want electron density pushed onto it? Or no, we want electron density withdrawn. And so the better it is as an electron pusher, which is going to weaken acidity. And so that's what we see here. We compare acetic acid versus octanoic acid, and it turns out that octanoic acid is weaker because there's more electron pushing going on. But is it significant? Well, it's 1.8 versus 1.3, so it's just slightly better. It's not hugely better. It's not hugely better because, the effect of having additional carbons diminishes with distance, the further out. I mean, this carbon's a minus 3, but it's so far out. Repeat that. The electron pushing part, or the?
You said it wasn't necessarily due to the carbons, but the distance.
No, it's both. The more carbons, the more electron rich. But it's a law of diminishing returns. You have more carbons, but they're getting further and further out. Therefore, I can add another carbon out here, but its impact is going to get weaker and weaker and weaker. It's like, they're talking about this is happening right now with the boosters, They're checking the antibody levels, and they say, okay, with the first booster, it provides maybe 1 month of pretty good protection, but now they're talking about what are they talking about? 4th booster now? But there's a law of diminishing returns because the levels drop off more dramatically, and so the impact is going to be weaker. Rather than 1 month, they're looking at weeks of effective protection. And so that kind of thing, the same kind of thing here happens. Yeah, we can add more and more carbons, and those are going to be electron rich, but the impact is going to be weaker and weaker as we get further and further out. There's a law of diminishing returns. All right, we have to shift our thinking. When we're thinking about acids, we think about positive. What makes it more positive? The hydrogen. When we're thinking about bases, we have to shift our thinking and go the opposite direction. This also deals with the conjugate relationship as well. And so before we do the amines, let's take a look at some bases now. you might recognize at all. And so one base would be this one. This is hypochlorite, which is the conjugate base. Hypochlorous acid. And let's compare that with hypobromite. Which one is going to be the stronger base? As the stronger base? Okay, which one would be more electron withdrawal? Okay, both chlorine and bromine are electron withdrawers because they're quite electronegative. They're highly electronegative. And so, which of these two would be more electron withdrawing, chlorine or bromine? Okay, it would be bromine because bromine is more electronegative than chlorine. Actually, which one would be the most electronegative element on the periodic table? The most electronegative element would be fluorine. So anything close to fluorine would be more. So chlorine is closer to fluorine, making it more electronegative. It also has to do with the size. Chlorine's smaller, bromine's bigger too. And so this one's more electronegative, which means it sucks. This is the inductive effect. It sucks electrons out and the negative charge away from oxygen. Bromine is also electronegative, but not as much. And so it's going to suck less. And so which one's going to have more negative charge concentrated on the oxygen? Well, both are negative one formal charge, but you know, there's a difference here. Well, the chlorine's trying to take away the negative charge, and it's more effective. And so this one has less negative charge buildup. And so in reality, and this one has more negative charge. It's electron withdrawing. And so this is going to be the stronger base. This one's going to be the weaker base because of the inductive effect, you know, chlorine versus bromine. Well, what about the acids? We were looking at the acids just a minute ago. When we look at the acids, which one's the stronger acid? Oops, did I get this right?
Yeah, that's what I was confused for a second. Is that supposed to be the other way around?
It's supposed to be the other way around. Sorry.
That's what I was like, wait.
You're right. Sorry. This is going to be the weaker base. It's going to be the weaker base because more of the negative charge is being withdrawn, right? And the base part is the oxygen here. Okay, now going to this one, which one is going to be the stronger acid?
The weaker base.
Okay, or, you know, because of the conjugate relationship, we know that the weaker the base, the stronger the acid. But why? Why would this one be the stronger acid?
Chlorine is more electronegative. So it's sucking more.
Yeah, right. Chlorine's sucking more of the electron cloud, which is making the hydrogen more positive. And so this one's going to have a higher positive charge, this one's going to have a lower positive charge. And so here we see the conjugate relationship in action. On the one hand, the high electronegativity of chlorine makes it a weaker species. On the other hand, high electronegativity of chlorine makes it a stronger species. And so it depends on the context of, are we looking at acids, bases, are we looking at electron withdrawing or electron pushing? Okay, so let's take a look at ammonia versus methylamine. If we look at the hydrogen, is hydrogen electron pushing or electron withdrawing? In one sense, it's electron pushing because hydrogen is a reducing agent. In another sense, you might think of it as neutral kind of thing. Or, the oxidation state of hydrogen is +1. In that sense, it could be electron withdrawing. Well, let's take a look at hydrogen versus having a methyl group. A methyl group we know is electron pushing or electron withdrawing. Electron pushing. And for bases, we want more negative charge on the nitrogen. Nitrogen is going to be the proton acceptor. And so in this case, which one's a stronger base? Ammonia or methylamine? Methylamine, because we have an electron pushing group on the nitrogen. It's going to be there. Okay, what about ethylamine? When we look at ethylamine, there are two carbons, electron-rich carbons. This one's going to be a -1, this one's going to be a -3. So we got these two carbons that are electron-rich pushing. And so ethylamine you would predict to be a better base than methylamine because we have more electron-rich carbons. However, countering that is the distance, because now we're at the beta, now the -3 carbons in the beta versus in the alpha position, but we got more carbons. And so the overall impact is not so significant. I mean, there's not a huge difference between methyl and ethyl because if you look at the PKBs, this is 338, this is 337. And so very small difference, but still ethylamine is more basic. How about bromamine? If we look at bromamine, this has a PKB of 761. It's not very basic at all. Why? Because to make things more basic, we want electron pushing groups. But bromine is not electron pushing. Bromine is electron withdrawer. And being an electron withdrawer is going to make it weaker. And so this is about 3 orders of magnitude, about 1,000 times weaker base by having that. In fact, pretty soon we stop calling the amine. So for example, if we have this nitrogen trifluoride, we don't call this trifluoroamine because this doesn't behave like an amine at all. We might call it chloramine if we have one chloride on there, chloro or chlorine on there. But this is not trifluoroamine, this is nitrogen trifluoride. And is nitrogen trifluoride a very good weak base? Is it a very good base? No, not at all. This is not basic at all. The PKB for this is very, very big, which means the KB for this is very, very small. And that's because, take a look at these. There are different ways we could do this. All these are delta minus on the nitrogens, although this one might have a delta plus or starting to have a delta plus. This one's actually going to be a delta plus because the fluorines are going to take the minus charges. Or we can just look at the oxidation states. When you look at the oxidation states, then you'll see that nitrogen is very electron. What is the oxidation state on this nitrogen here? Well, it's got 0, 0, 0, 2. So it's got 2 electrons. Nitrogen is supposed to have 5 electrons. So it's missing 3 electrons, which means it's going to be +3 or -3. If it's missing 3 electrons, is it going to be +3 or -3? It's going to be +3. Versus ammonia. What's the oxidation state on ammonia? If we look at ammonia over here, two, 4, 6, 8. Ammonia is going to be -3 oxidation state. And so it's going -3 to +3. Well, this one's going to be a heck of a lot less basic. This one's going to be significantly more basic. What's the oxidation state on nitrogen here? 2, 4, 6, 7. 2, 4, 6, 7 -2. Same thing here. 2, 4, 6, 7 -2. So these are going to be quite a bit more basic. This one's going to be 2, 4, 6. This is only -1. Here's the benzene ring. This is the shorthand way of representing the benzene ring. And there's two ways of depicting the electron cloud density being spread out. One way is, I had a delocalized electron cloud above the ring and below the ring, and it can accommodate more electron cloud. Another way is to show it mechanistically here. And what they're showing here is that this is called phenylamine, or they have another name for this, aniline. Aniline here. And so if we look at phenylamine or aniline, phenyl, this is called phenyl group, and the amine group, phenylamine or aniline. Aniline is this common name. If we look at aniline, two ways of thinking about this. We have, this delocalized electron cloud here and delocalized electron cloud underneath. And that can accommodate electron cloud density. Or another way is mechanistically. If we take this lone pair here, and this is something you should review from Chem 1A, is hybridization. Do you know what the hybridization on that nitrogen is there? Phenylamine. So actually, let's draw it out. So we draw out the benzene ring. This is all trigonal planar carbons, and this forms like a flat pancake-like molecule. And we have alternating double and single bonds. It's called conjugation. It's called an aromatic. Aromatics have this alternating single double bond or conjugated bond network. And then we have this. So what is the hybridization on this nitrogen here? Hybridization is depending on how many groups of electrons we have. And so we have, this is one way, depending on how many groups of electrons. Each group is going to take up, so this would be, we have 4 groups. It would be S, P, 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 sp3. This is sp3. This is tetrahedral, electron geometry, trigonal, pyramidal, molecular geometry. What about this carbon here? Well, there are 3 groups, so it would be sp2 hybridized. As sp2 hybridized, we're going to have unhybridized p orbitals. This is, if you go into organic chemistry, you need to review this. In fact, start reviewing it now because it's useful for regular chem too. This is chapter 11. So we look at chapter 11 and we look at benzene chapter. And so there's a whole section on bonding in benzene. The bonding in benzene is very special. Because of this total complete delocalization of the pi bonding network, it's much stronger. It's much stronger than what would be predicted by bond order of 1.5. Not, And so what we have is we have these PP pi bond here that can be delocalized over the entire benzene ring structure. And so this is showing that pi bonds being delocalized over the entire ring structure. Delocalized pi bonding. It's a take-home message there. And that creates a stable structure. Okay. So these are sp2. And so you can see sp2 sigma bonds. Do you see that? sp2 sigmas. So this is the sigma bonding network. And then we have a pi bonding. And the pi bonding is delocalized over the entire structure. That's So what we're going to do is we're going to show this mechanistically. And mechanisms are very popular in organic chemistry. What we do with mechanisms is we just rearrange the electrons. So what we can do is we can try to delocalize some of the electron density from the nitrogen into the ring. One way to do that is to drop this lone pair into the bond here and make a double bond. But if we make a double bond here, that's a double bond, single bond, that's 5 bonds. Carbon cannot have an expanded octet, because that's the octet law for carbon and nitrogen are oxygen. It's a law, it's not a rule. And so we don't have an expanded octet here. And so one way to fix that is, I should have done it the other way. One way to fix that is to break one of these pi bonds and place the pi bonding electrons onto that carbon here. And so this is inverted from the picture in your book. Sorry, you redrew it. I don't want you to make you redraw it. And so we end up with this structure that looks like this. So what we have is we no longer have a lone pair on the nitrogen. And so what happened here is this nitrogen went from sp3 hybridized. Now it's going to be sp4 well, sp2 hybridized. sp2.
I thought you said you count each of the bonds, right?
Yeah, well, each group. And so this would be spt, each group of electrons.
Got it.
There's going to be one unhybridized p orbital. This one would be sp.
SP2.
Well, lone pair counts as a group. So SPPP would be SP.
SP4.
No, this would be S and then PPP, triple P, so SP3. Right?
Can't count it.
That's what it should be. But oddly enough, this one doesn't come out sp3 hybridized. You know what the hybridization of this one comes out to? We do sp3 hybridization to minimize the repulsions. And so when we do sp3 hybridization, we have 4 groups. And the 4 groups, to get as far apart as possible, adopt the tetrahedral configuration. That's sp3. But in this case, what we're going to do is we're going to retain sp2 hybridization. And so we'll have these trigonal-planar sp2 orbitals, and then we're going to have one unhybridized p orbital. One unhybridized p orbital will just be stuck in the center like this. And that's where the lone pair goes. The lone pair is going to stay in sp2. I mean, these are going to stay sp2 here. That lone pair is actually going to go into an sp3, but it's going to create larger repulsions if that lone pair stays in sp3. So that lone pair stays in sp3. What am I talking about? Sorry. The lone pair stays in the P. Well, the lone pair stays in the P because what we're going to do is we're going to have all these P orbitals now lined up. And so we can delocalize them. Over like that. And so it retains that hybridization. And then this carbon gains a negative charge here. Charge. That should be in P orbital. You don't have to draw that. So let's go back to, we're looking at 16. So this is what I'm trying to show, except they went to this top carbon, I went to the bottom carbon, but it doesn't really matter here because I drew the double bonds in the alternate positions here. But the point of this is to show that what we can do is we can spread out the force density. So if I take that lone pair and drop it into the bond here, I'll create a double bond there. But that's going to create too many bonds to this carbon here, so this double bond has to be kicked out, putting the pair of electrons there. And then I can drop these into the bond here and kick them out up here. And so these are called resonance forms here. And these resonance forms show that we can delocalize the electron cloud via resonance into the structure, into benzene ring. And so what we think is going to be an electron pusher, because hydrocarbons like benzene, you would suspect these to be electron pushers, turns out to be an electron withdrawer. And so if we have an electron withdrawer, the benzene ring here on an amine, is that going to make it more basic or less basic?
Looks like we have an electron pusher on
Is this, the benzene ring is going to be an electron withdrawer. We think it's a pusher because it's carbon and hydrogen, but it turns out to be an electron withdrawer because of the delocalized pi bonding network, or because we can distribute more electron density within the ring via this mechanism. And so is this going to, if this is an electron withdrawer, is it going to make it more basic or less basic? Electron withdrawer.
maybe less basic.
It would be less basic. And so aniline is a lot less basic. And so when we compare aniline, here, look at the pKb is 9.13, which is not very basic. Compared to cyclohexylamine, cyclohexylamine has a pKb of 3.36. So the cyclohexane group is an electron pusher. The benzene group is electron withdrawal. Both of these contain 6 carbon atoms in the ring. It's just because of the delocalized pi bonding network here versus we have localized bonds here. Now, what we're going to have here is the electron withdrawing groups here. We have electron withdrawing groups in the pair positions here, furthest away, or the positions closest to the mean. And so if we throw on a chlorine on the benzene, benzene's already an electron withdrawal, but with a chlorine attached to it, it's going to be a better electron withdrawal or worse electron withdrawal. Here. Well, chlorine's electronegative, so chlorine is going to pull electron density towards it, which is going to take electron density away from the benzene ring, so it's going to make it an even better electron withdrawal. So when we compare aniline here to orthochloroaniline, we can see orthochloroaniline is a much worse base than aniline. And why is that? Because it's even better electron withdrawal, which makes the nitrogen even less negative. We want more negative nitrogen. The para is not going to have as big of an impact. Para is still worse. But the para suffers from distance here. You know, the further the distance, the less of an impact it has. The closer the distance, the more of an impact it has. Now the meta, which is not shown here, is somewhere in between here, 1066. Okay. And so the meta is a little bit weaker than the para, which is odd, but a little bit stronger than the ortho. But for meta, we would have expected it to be, oh yeah, actually that makes sense. Let's leave it at that. Okay, that's the opposite effect. When we do acids, we have to shift our thinking now. And so let's go back to these acids. Remember these acids, phenol? This was an unusually strong acid because alcohols aren't acidic. They're extremely weak acids. And so when we look at phenol, phenol is much stronger than your typical alcohol. Your typical alcohol is going to be extremely weak. And the reason is because phenol is an electron withdrawer, making the acid stronger. And orthochlorophenol is an even better electron withdrawal, making the acid even better. Okay, here's looking at the stability of the conjugate base. Yeah. Maybe we'll take a look at the stability of the conjugate base a little bit later. What I want to do is I want to talk about this last section, Lewis acids and bases here. And so a Lewis acid is an electron pair acceptor, a Lewis base is electron pair donor. And so ammonia is our Lewis base here. Boron trifluoride does not form an octet. It could form an octet if we take a lone pair here and drop it into the bond, but fluorine will never do that. Fluorine's never going to share. Because if it shares this to form a double bond, it makes fluorine positive and boron negative. And that's not going to happen. And so we're less than an octet, which makes this an excellent Lewis acid. Because if there's a lone pair that can be donated from a Lewis base, then we can complete the octet on boron, which we do here. And boron gets a negative charge, but it's taking it from nitrogen. Nitrogen's donating it, so it's going to get a positive charge. Fluorines wouldn't do that. And so what we form is a coordinate covalent bond. And the same thing here. This would be a Lewis acid-base reaction here. The oxide here is our Lewis base, electron pair donor. Sulfur dioxide here is going to be our Lewis acid. And so it's going to accept a lone pair to form a bond. This bond is called a coordinate covalent bond or David bond. Both bonding electrons come from one atom. Here's an example of a Bronsted acid-base reaction or Lewis acid-base reaction. And so in this case, these waters here, ligands, the aqua ligands, are much more acidic than what we normally expect. And the reason why these are much more acidic is because of aluminum. Aluminum is +3. And so aluminum +3 is going to have a large inductive effect, sucking electron density away from water, making these hydrogens much more acidic than they normally are. And so when we look at hexa-aqua aluminum 3 ion, hexa-aqua aluminum 3 ion is shown here, and it has a Ka of 10 to the minus 5, which means it's just slightly less acidic than acetic acid, but more acidic than carbonic acid. You see that? Yeah. And so this is a pretty decent acid. It's a pretty decent acid because of the electron withdrawing effect of the aluminum 3 ion, making these hydrogens much more positive. And so water can come along and pluck that proton off. If it plucks that proton off, we form hydronium and hydroxide. And so we'll have hydroxyl ligand there. And so this is the equation here. We have the hexa-aqua complex. Water comes along. This is the Ka equation. Ka produces hydronium. And in this case, what's the name of this? This would be penta, aqua,
hydroxide.
Yeah, hydroxido or hydroxo.
Aluminum.
Aluminum. Any charge on aluminum? 3. And so this is the Ka equation, and this Ka is 10 to the minus 5, which is pretty good. So Ka is 10 to the minus 5. They say the Ka value is essentially the same as that of acetic acid, so this is comparable to acetic acid. Okay, we also have Lewis acid-base reactions in the formation of these complexes here. And so to form the hexa-aqua complex, we had a Lewis acid-base reaction between the aluminum and the ligands here. And so the waters come along, they donate one lone pair to the aluminum to form the octahedral complex that we see here. Okay, aluminum ion is a pretty good Lewis acid, and water is a decent Lewis base. Let's take a look at some other Lewis acids, the metal cations here. And so we go to this section here, which is why does sodium ion not act as an acid and make a solution? Aluminum does act as an acid, and you can see the Al3 plus is acidic acetic acid in water, but sodium ion is neutral. And it has to do with charge density, the charge over the volume, charge density. sodium ions and other group 1 species don't have a very high charge density, and therefore they aren't very acidic. So when we look at sodium ions, its pKa is 14.2, which is worse than water. Water's pKa is 14. And so sodium ions we think of those as neutral. And you can see the group 1s are like that. Also group 2s, if we look at calcium, calcium's pK is 12.8. It's not very acidic. And so those are. But if we look at aluminum, aluminum is pretty acidic. Aluminum has a pK of 5, and it's very small, highly charged. The most acidic of these is iron 3. Iron 3 is going to have a pKa of 2.2. In fact, if we look at the hexaoctal complex of iron 3, look here, you can see that the Ka value they give for us is 6 times 10 minus 3, which is quite a bit more acidic than acetic acid, 100 times more acidic than acetic acid. And so this has to do with charge density. So these highly charged small ions are very acidic. And so what they try to do is they try to do a correlation between the acid strength and the charge density here. And so the higher the charge density, the more acidic you expect it to be. So that's what we see here, the correlation. The higher the charge density, the more acidic, you know. But the correlation kind of breaks down here. And you get to these very high charge densities. And that's because there are other factors in addition, like covalent bonding interactions and that type of stuff. And so when we think about metal cations, not all metal cations are very acidic. Like the group 1s, we ignore those. And some of the group 2s we ignore. Except for beryllium. Beryllium's, you know, highly charged and very small. And so it has a very high charge density. Its acidity is quite high. But the other group 2, like calcium, strontium, barium, not very acidic at all. Okay, now metal cations can act as Lewis acids in formations of complexes, but let's look at some other Lewis acid-based reactions, not in the context of formation of complexes. And so, just take a look here. Actually, I don't have it right here. So in Chem 1A, there's a saying, and the saying went like this: metal oxides are basic. Non-metal oxides are acidic. So here we have a metal oxide that's basic. Here we have a non-metal oxide that's an acid. And so this is a Lewis acid-base reaction. Okay, what we're going to do is we're going to analyze that more in the context of Lewis acid-base, rather than in memorizing something like that. And so Chem 1A, you memorize, maybe some of you memorize that metal oxides are acidic, non-metal oxides metal oxides are basic, non-metal oxides are acidic, and semi-metal oxides, like aluminum oxide, are amphoteric. And so let's take calcium oxide as an example here. And so we'll draw out the Lewis structure of calcium oxide, which is just going to have a lattice of ions. Like so. Etc. This goes on. Let's call this the surface here. So we have our base. Actually, it's more than a base, because when we analyze it, we analyze it atom by atom. And so, yes, this is metal oxide. Yes, it's going to be basic, but there's also an acid. And what is the acid in this calcium oxide? The acid is, well, the oxygen is the base here, the oxide. In fact, oxide, what ranking is oxide as the Bronsted base? When we look at the Bronsted acid base chart here, oxide is the number 2 base. Anode is number 1, oxide is number 2. So oxide is a great base. So when we rank it here, we rank it above hydroxide. Oxide is an even better base than hydroxide. Hydroxide is a better base than water. You see the concentration of negative charge. The calcium ions are acid. Are calcium ions very good acid? Well, let's take a look at the chart there. Would we even consider calcium ions as being very acidic? No. I mean, the pKa is pretty high. And so it's not very good at all. And so we can kind of ignore it. And so we do the same thing for water. Water is both an acid and a base. And so I have water like this. All right, what's the acid part of water? The acid part of water are going to be the hydrogens. And the base part of water is going to be the oxygen. And so Lewis base is electron pair donor with negative charge density. And so that's oxygen. And then Lewis acid is electron pair acceptor. But the problem is here is, can this really accept an electron pair? So let's say I have my base here. This is the base site. Attack my acid site here. What can happen? Well, what has to happen is the water has to slam into this because the oxygens are locked in the lattice. But what's going to happen here is this. This sp3 lone pair gets pushed into the s. This is an s-sp3 sigma bond. And so as this sp3 lone pair gets pushed into the s orbital here, it's going to kick out the electrons from the sp3s sigma bond onto the oxygen. Yeah. So what we're going to form is this. That oxygen is going to take up that hydrogen that was once on the water. And so we're going to form a hydroxide now in the lattice. And that water is going to lose that hydrogen to form another hydroxide here. Okay. So basically what results is this. We have calcium oxide solid plus water. This is going to go to calcium hydroxide. Now calcium hydroxide is soluble. Hydroxides are all insoluble except for group 1 ammonium and calcium strontium diarrhea. And so this would be a Lewis acid-base reaction here. Okay. So are we out of time? Yeah. All right, stop here. Thanks. And then we'll look at one more. We're just about done. In fact, I'm going to finish it tomorrow. So tomorrow, let's meet in the lab first. We're going to look at the crystals and see how they're doing.